First, let us take a look at the first technique to fight overfitting, which is penalization. The idea of penalization is quite simple. Say that you have an optimization problem in which your aim is to minimize the loss L, which depends on theta x, y, where x and y stands for the data, inputs and outputs, and theta is a parameter you want to optimize. You want to find the best theta which satisfies some conditions, which is equivalent to solving the constraint optimization problem in equation 14. The penalization function pen stands for the type of constraints you put on theta. It can be shown that this problem is equivalent to the optimization problem written in 15, which is an unconstrained optimization problem. There is only one objective function to minimize without additional constraints. The dependence between the constant in equation 14 and lambda in equation 15 is unfortunately not explicit in general. The problem in 15 is quite common. The first term is a loss term, which depends on the data set. The second term is a penalization term, which enforces some structure on the parameters. Finally, lambda is a penalization constant, which controls the strength of the penalization. Setting this constant to 0 leads to the classic unconstrained problem, whereas setting this constant very large amounts to finding theta, minimizing the penalization term only. The null vector is often a minimizer of this penalization term. Therefore, a trade-off is needed and the constant lambda must be chosen carefully. In neural network, we often penalize the weights but not the biases, since the biases lead to less instability saturation phenomenon than the weights. Some examples of penalization are typically LP norms leading to ridge, lasso, or elastic net procedures. Choosing different penalization leads to different structures on theta. For example, an L2 penalization will lead to a solution for theta which has small components. A L1 penalization will lead to a sparse solution for theta, meaning that many coefficients of theta will be equal to 0. A combination of both L1 and L2 norm inherit of both their characteristics, namely small and sparse coefficients. We are going to use a linear model to see the precise impact of penalization, since we can easily derive the expressions of the different estimates for this model. So we consider here the linear regression estimate beta hat, which is given by this formulation, which is nothing but a sum of squares. This problem can be written in a matrix formulation as in equation 17. A classic exercise is to show that the solution of this problem can be expressed as in equation 18. Instead of finding beta hat, which is a solution of the previous problem, we can define the penalized problem for any norm LQ and denote by beta hat lambda q the solution of this penalized problem. Note that if you take q equal to 2, you find the ridge linear regression problem, and if you take q equal to 1, you find the lasso. Let's start with q equal to 2. As for the linear regression problem, you can show that this problem admits a solution, and the exact expression of the solution is given by the formula 19. If you make some additional assumptions on the design matrix, you obtain a very simple expression for each coefficient of the ridge regression estimate beta hat, which is given by equation 20. This expression highlights that the coefficients beta hat lambda 2 are smaller than the original coefficients beta hat, which are the coefficients given by the linear regression. This proves exactly what we stated explicitly before, that is the fact that applying a L2 penalization leads to smaller coefficients. Looking at equation 19, you see that solving the ridge regression problem involves inverting a matrix of the form x prime x plus lambda identity, whereas the original least squares problem involves inverting x prime x. If x prime x has very small eigenvalues, that is, if there is some strong correlation in the variables, inverting x prime x is numerically unstable. Solving the penalized problem with an L2 norm circumvents this issue by inverting instead x prime x plus lambda identity, which is easier numerically for lambda large enough. Therefore, the L2 penalization also eases the optimization procedure in presence of correlation. This precise derivation holds for linear problems only.